All right. Good evening, everyone. Good evening to you. Good evening. Good evening. It's good to be back. I hope our week has been fantastic. I hope we've had a great week, and the weather has not been a bother. I know it's a bit hot here in Nigeria. For those of us in other nation, I don't know how is it, but Nigeria is a bit hot at the moment. Uh, I think we'll just full up by drinking water. So today we'll be looking at feature scaling. I know Isaac spoke about feature engineering. Yes. Good evening, Stephen. Good evening, Benjamin. Good evening, Chrisley, Dami, Omoni, Olanike, Isaac. Good evening, Natalie. Good evening. Good evening. It's good to have everyone back. It's a beautiful week. Yeah, it's warm here. Oh, fantastic. Fantastic. It's hot here. I just have to put on this shirt. I have no choice. It's hot. But anyway, we'll scale through. All right. So we are going through what is feature scaling. And I'll be talking about two fantastic methods for feature scaling. I know on Monday, Isaac spoke about a bit of feature engineering. He spoke about Z-score. I'm just going to be elaborating on that. He spoke about outliers and things like that. So I'm just going to give us the theoretical background of those things that we did on Monday. Look at them just for us to understand when we need to do that. We're not talking about working on our data sets. So when you work on your data set, so that it gives you the required standardization, the required generalizability. When we talk of generalizability, talking that what your data set is well cleaned, well um, arranged, well classified, so that by the time you are training your model, you have no issues at all. So that's what we're actually talking about. So I say feature scaling is a technique used to bring all features in a data set to the same scale or range. Yes, I know Isaac spoke about that thoroughly, and I'm just going to be reiterating that also. Yes, for your model to be able to fit well, for your model to perform what it needs to perform, or what you have decided the end product of your model, your data set that you're going to use in training that model must fall on the same scale and range. Because if you have those issues and they are not on the same scale and range, that's where the problem of what we call underfitting and overfitting comes in. When we talk of overfitting, it means that your model is underperforming. Then when we talk about overfitting, it means that what your model is overperforming. As we all know that there's no machine or model that can be 100%. When you look at the theory of the Carnot engine theory, for those of us that are physicists, it says what no machine, no engine, no model can ever but attain 100% accuracy. We're just trying to. There's no human being that is 100%. So definitely, there's no way machine also can be what 100%. But there are ranges that classifies, or that there are classification ranges that have been given. And we know, okay, between this and this, definitely, yes, this model is actually working. In fact, you might not even use ranges for your models. It might just be that I've tested with my own set of data. Then you need external data sets to come in. You need those external data sets to actually make sure that your model is working for. And if your model appear maybe for your metrics is that when external data sets are being used, then my model needs to come between the range of maybe I have trained with my own data. I got an accuracy between 80 and 90. So if I'm coming up with an external data set, the data that my system hasn't seen, my model hasn't come across before, and I'm getting 91. So it means that yes, my model is actually what generalizable based on what I've done on my data set. All right. So that's about feature scaling. I just put this little diagram for us to see. So what we are talking about is that you can see the way this data set are scattered. They're scattered all around. So when we're talking of scaling, we're bringing them to what? To come together to the same range. To come together to the same range, and then so that we can actually what? Use the data to classify, to train our model to give us what our expected right. So let's keep going. Thank you very much. All right. So next, why do we need feature scaling? Why do we need a feature scaling? I think one of the basic reasons why we need feature scaling is what we want to ensure that all the features from our data set contribute equally to your model training. Exactly. So that there's no discrepancy at all. One feature is not overshadowing another another feature. It's just that. Then we want to improve the convergence speed and the optimization of our algorithms like the gradient descent. Yes, we need to look at that because that's also if your data is not well scaled, if the features in your data are not well scaled, then you might have problem in the speed in your optimization. That's why you find out that somebody builds a model that can predict diseases or classify diseases, and then all of a sudden you are finding out that wow, its model is working in less than 30 seconds or let's say 1 minute. And you bring up another model and it's taking close to 5 minutes or thereabout, and you're wondering what's going on. Then essential for distance-based model is when you're using distance-based model. Uh, when you have like your KNN, okay, your nearest nested loop, you have your SVM, your support vector machine, and your k-means, you're looking at those kind of models. Then you want to prevent domination by large scale features. Exactly. Like I said, a feature must not overshadow another feature. So when the more we get into it, I'll start showing us that there are some other means. It's more than talking about normalization and standardization today. We have things like the ANOVA for feature engineering. You have your ANOVA, you have your what's it called? So those kind of feature engineering models, they are just like mathematical things that picks best features that won't overshadow the other feature for the training of your model. So that's the reason why we are doing feature scaling. We just want to make sure that we are balanced so there's no bias. So that's the best one. There's no bias at all. No bias in our training. All right. Then you improves your interpretability of coefficients in linear model. What does that mean? Your model is interpretable. Anybody can pick your model and understand, oh, this is what this is doing. Oh, this is the feature that has, these are features that have affected this model to perform this way. These are features that if you have not scaled them or brought them into the same way with other ones, it will have affected our final performance. Then we want to stabilize model performance across all data sets, like what I said earlier on. That's the reason. In fact, that's one of the major reasons why we're doing what we're doing. We want to make sure that what? Yeah, yeah. Okay, hold on. Somebody is saying my Spain is not clear. Can somebody else help me support that notion in our work? You might need to check your network because I'm actually viewing on my other device and I can see I can see my screen as clear as possible. I'm using my other device. I can see my screen also. But every time we try as much as possible to set up a second device so I'll be sure that you are seeing what I'm seeing. If you're having that issue, you might need to check your internet connection. All right, so it is clear. Thank you very much, Favor. So internet is internet, Deborah. Your internet connectivity is it's Abiodun's pen is clear here. And for Deborah, it is clear also. I'm sorry, it is clear from here. So I've changed my video quality. It's at 1080. I've increased the resolution to the last. Check your internet. Thank you very much. Thank you. All right, let's go on. Then you need for your what? For your principal what? I said required for PCA, and other dimensionalities. Other dimensionality. Okay, let me pause so that whoever is having issue, let's sort that out and we quickly go on to what we need to do. So I'm going to start today. So check. It's our let me just pause. Yeah, it's clear, it's clear. Screen is blurry. Okay, kindly check your like I'll say again, check your what's it called? check your network connection. Check your network connection. I've refreshed my screen to be able to make sure that we are doing we're on the right page. All right. Okay. That thing is clear because it's clear. All right. Thank you very much, everyone. If you're good to, you're good to go. Good to go. All right. I've adjusted also. It's faded. No issues, please. Thank you. Thank you. Thank you. You can see my slides. Appreciate that. Okay. Let's hold on. Also, I'm also doing some adjustment also. Let me just so that I want everybody to do because these are things that we need to know. So that when you get to your practical class, you don't have issues at all. You're just swimming and you're doing very fantastic. Right. Right. Okay. All right. Okay. Let's go. Let's go. So full meaning of PCA. Yeah, that is called the principal component analysis. Principal component analysis. Just transforming the original features in your data set to a new set of features. That's what we call. So that you pick what? You pick the components based on the amount of variance that they capture from your data. So what are you doing there? You are reducing dimensionality, but you are preserving as much as variance as possible. I'm sure as this spoke about variance on Monday. You are helping so that your visualization is fantastic. Then you can speed up your machine learning algorithm. And you are removing what do you call them? Outliers in your features. So that is just principal component analysis. All right. All right. So thank you. Thank you. Steven, thank you. All right. Then we want to boost accuracy, like I said, and efficiency in our machine learning models. We want to build efficiency. We want to make sure that our accuracy is fantastic. We don't want to just we don't want to waste what's it called? We don't just want to waste the data sets because after you've gotten a lot of large data sets, some data sets are close to 15,000. We are wondering, oh, what do I need to do? So we must make sure. That's just the reason for future future scaling. All right, let's go on. Thank you, everyone. Thank you for your patience. So we'll be looking at these two concepts, as I said earlier on. I'll be talking about standardization and normalization. Normalization. All right. So normalization is called the max scaling. Mean max scaling. So what we are doing is that you see the formula is looking at the minimum value and the what and the maximum value. So I said it rescales the value of your feature to a range of 0 to 1. So thereby maintaining what we call your relative distribution. So yeah, the formula is going to be in the next class. So the formula ensures that all values lie between 0 and 1. All the values, what you are doing is that everything I do, anything that goes below 0 and goes above 1 becomes what a problem for you. So you try to align it to give you what you need. What you need. All right, please hold on. Okay, I've okay. I need to hold on this. Admin, can you kindly give us a break of 2 minutes, please? This slide, so I can take my slide from my end. The slide that is being projected is incomplete. I don't know what's going on. What I have with me is different from what is being projected. This 2 minutes. Please bear with us for the next 2 minutes. Thank you. Please allow me to share my screen myself, please. What you have up is I don't know what's happening. It's not what I have here. Some things are missing. I'm not seeing them in that slide, which is surprising. Thank you. Thank you very much. Hold on, please. Share my screen. We're almost there. Almost there. Just give me 2 minutes more. We're back to our place. Sorry about this. No problem. I'll share my entire screen. Let me share my entire screen. Okay. All right. You can see my screen. Fantastic. Let me share my slides. Okay. Can we all see my slide, please? I think so. You can see my slide. Just give me a thumbs up. Let me connect to my second device also, so I can see our comments. Thank you. All right. Let's hold on. So I can see our comments. Okay. Fantastic. Thank you. Thank you. Yes. Yes. Fantastic. So let's get back. Thank you very much. Our comments. Okay. Fantastic. Great. So I was calling. I said normalization talks about what you call the main mass scaling. Then it rescales your values to the range of 0 and 1. So it means that anything you have below 0 is an outlier. It is a problem to your data feature. Anything you have above 1 is also a problem. So it's trying to maintain what you call a relative distribution. A relative distribution. And you can see the formula here. You can see. So your formula says what? X normal. So your normal range, which is equals to what? Your x is your either your minimum value or your maximum value minus your minimum value, then divided by what? Your maximum value, yes, minus what? Your minimum value. When we get there, you will see it. There's an example I've actually created. So this is your formula for normalization. This is a formula for normalization. So just imagine why we are doing when we talk about pandas and numpy. Just imagine that you need to calculate and normalize about. You have a data set that has about close to 15,000 features, and also yeah, exactly 15,000 data there about yes of 15,000 data set for maybe different patients of like yes, let's say 15,000 patients. And you have about 28 features. So you need to normalize about out of the 15,000 patients, you realize that about 10,000 of them, yeah, it's not being normalized the way you want it to be. They are falling below and above, and you need to do this just using this linear calculation. You know how difficult it's going to be to begin to calculate for over 10,000 patients. It means that you take each patient one after the other and you begin to calculate for. I'm telling you, in the next 1 week, you are still there because you will get bored. But just imagine just by a simple line of code, the standardization or normalization, you get this, you get it done. Very clear now. All right. Thank you. Normal value. Fantastic. All right. So when do I use normalization? That's the question. Because we are not just talking about this and we are just I tell people you must understand why you're using a particular feature, a particular what's it called, a particular node of code exactly. Because most of the times you want to perform something, some functions, and you don't just pick any formula because it's being used. You must understand the reason why you are doing that. Number one is what when your features have what different ranges. And I think that's one of the first things that they mentioned and we'll be talking about. Says what? It mustn't fall what below zero and it mustn't be what above one. So you are looking at that between that range. You must have that range. Then when the algorithm requires bounded inputs, yes, we are working with like neural networks. Very soon we'll be getting to there when we'll be talking more of neural networks, talking about your CNN, evolutional neural networks, having to deal with things like deep learning. And now we're still in what? We're still talking about machine learning. Exactly. So when we move into AI, you need to see things like that. But when your data is not what? Gaussian distributed. When your data is not Gaussian distributed. All right. So you begin to see that. So and now, because I know somebody will say, oh, what is Gaussian distributed? Don't let it don't get scared. It means that your data is skewed. When your data when you mean something is Gaussian or Bayesian distributed, your data is skewed. It might be as a long tail on one side, and the other side is not. Or maybe it's bimodal. Exactly. You have two. When you mean bimodal, two different kind of states or two peaks. Then as outliers or everything, yes. We're talking about outliers. We talk about outliers before the end of the class. What are outliers? Outliers are like stray sheets. You have 100 sheep and one sheep is running away. So outliers are like that. Let me use the word we use. We say the black sheep exactly. The black sheep. You have white sheep, male and female, gave birth to 10 sheep, and out of them, one of them is black, others are white. So that's like just like an outline. Then maybe it's uniform. You see, there's a uniform. All values just alike. And it's very impossible when you're having this step of data, everything is being the same. And then something is wrong somewhere. Or maybe it might be exponential, it might be Gaussian, or log normal in shape. And these are all polynomials or exactly so. These are just extensively. So when you hear Gaussian distributed, it's just like it's not fitting in. It's not fitting in. I think Jackson have been able to answer your question. If I can see it here. What is Gaussian distribution? Okay. So just when your data has these five what's it called attributes. Attributes. All right. So this is your code for normalization. So everything we teach by Friday, blessing will carry it out so you understand. So number one, you need what you call your scikit learn, or what you call your scikit exactly. A library called scikit learn. So you call that pre-processing because normalization is like a pre-processing uh, feature. Exactly. After we've spoken about data collection. Exactly. How do you retrieve your data set? The next stage after retrieving your data set is what we call preprocessing. Another preprocessing is where you have everything like your data cleaning, your features scaling, your feature normalization, things like that, standardization, um, 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 anything that has to do with cleaning your data to just make sure that what the data gives you the required attributes that you need. Everything falls under what you call data preprocessing. So as we go on, you will see when we get to the class, I will list everything for you. You will now see that you have almost about 7 to 8 steps from your data acquisition, which we call data collection, to your data preprocessing, to your test test training test split, to your model selection, to your model training, to your model evaluation, to your model validation, to your model testing also. When you talk about validation, you're the one doing that, that's internal. So you train, you validate using when you maybe you've gotten a set of data set, 15,000, you pick like 13,000, use it to train the model, then you now test with the remaining 2,000 that has not been trained at all to be sure that your model itself can identify. Then you now do external testing, which you go out to get from somewhere else and be sure, okay, now I'm not using my own data set. Somebody bring your own data data set. Bring your data set. Let's use it to test my model. If it works out fine, then it means that my model can work on different data sets. Then you have people put deployment. You might not need to deploy. That's where AI comes in. And that's everything you are going to be doing even when you're doing your project. If you deploy your project, you are not just going to build a model, be able to deploy maybe as a web interface or something that we'll be able to use and test. So it's not just alone creating a model. The model should be deployed. Should be able to use it to solve the problem to be sure okay, is it actually solving the problem I want to solve. So for normalization, you call it and import your min max scalar. So that's it. You know, I told us that it's called min max. Exactly. So for Python, we don't call it normalization, we call it the min max scaling. So it brings it, you have your data here, which is 5, 10, and this is your original data. So you want to scale the data to fall between 0 and not lower than, not less than 0 and not greater than 1. So you have your scalar, which is equal to your min max scalar, which you are creating the scalar now. Then scaled is equal to scale dot fit feature transform. So you are fitting the scalar to the data, and you transform it, and you now print what the scaled data. So you scale this data and change them to the range of what zeros and one and one. You see how we did that in this place. I'll show you the manual way, and also when on Friday, lesson will show you how to use the system to your Python programming environment to do that also. So this is what it means. Normalization. Example. We have original data here, which are 3, 5, 10, and 15. If I ask you which is the minimum, you should know which is the minimum. And if I ask you which is the maximum here, you should know which is the maximum. So basically from here, we know that 5 is the minimum range, and then 15 is the maximum. So I said normalize the above using this formula that you have. Your normal value with your x. Your x is any one of these that you are using. Your x is this. So mean, we already know our mean, which we need here. We already know our max value, which we need for this formula. So let's go in there. So this is what is there. See for x, so you pick them one after the other. That's what that what's it called? Normalization. Um, what's it called? Normalization code in Python is doing. But now we are doing it manually. Manually. So I pick 5, the lowest one. So and you remember our formula says what x. So this is our x, which is 5. Minus what? X minimum. Our x minimum is also 5. Divided by what? X maximum minus what? X minimum. So when we look at it, 0 divided by 0 will always be 0. So the first normalized data is 0. All right, class, can we do for 10 and 15 quickly? In the next 3 minutes, let's calculate for 10 and 15. Okay, as somebody is already finished, I will hold on. I want other people to do that quickly. I just want to be sure that you understand what I'm saying. If I don't, and that's why I said, hold on, go on. Deborah, do yours. Let me see. Uh, uh, I know where you are saying it is wrong. I know that 15. Just go on, please. I understand you. 0 over 10. If I put 0 over 0 there, if I put 0 over 10, 0 over 10 is still 0. So, you can't divide anything by. So do the class work, please. So calculate for 10 and 15. Thank you. I've seen my error. Thank you very much. It's supposed to be 15 minus 5 is 10. I get you. Thank you. Please, the class work, please. Let me know what is your value for 10 and 15. 10 and 15. Thank you. Thank you. Let's go on, please. I'm waiting for our answers. Thank you, Deborah. I appreciate it. Okay. 0.5, 0.51. Fantastic. So it means that we are following. So 0.5 and 0.5 and 1, 0.5 and 1. Exactly. 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 So that is great. That is great. So it means you can see now that our normalized scale, by the time you add these answers here, you are going to be having what 0, 0.5, and 1. So you can see that it's still between what our scale. When we're talking about normalization, it must always fall between what the scale not lesser than 0 and not what's greater than 1. And when you look at the values we've gotten for 5, 10, and 15, it is 0, 0.5, and 1. Well, thank you, everyone. Thank you very everyone. Fantastic. Fantastic. So that's what your min mass scalar code in Python is doing. So, but it has been gotten for is a mathematical formula that you need to do. But now you writing for it in your Python code allows you to carry out min mass scaling for data set of over 15,000. But I don't want us to see it because I've been in a class and somebody was like, "Sir, it's like you are doing magic." So for this your class, I decided I said, "For everything I've learned from training different set of people, we need to bring it together. So see what is happening. There's no magic behind it. Something is going on from underneath it. So nobody just brought up a formula. There's a mathematical formula for that, and it can be practiced with simply. So that's why I just use for 5. Thank you, everyone. You have done very well. You have done that. If you have somebody said, what if it is more than 1 or less? Yes, when you begin to, but if you follow this, what's it called? The main reason why we are even doing this is because we have some values that are falling from below what, yeah, below or what or above. Exactly. So when you're having those kind of values, that's why we are normalizing them. So you pick a range. You just pick a range. When we are doing the practical, you see what we mean. You see, you yourself, you will know. You just pick a range and say, okay, let this fall between this and this. Let this fall between this and this. So you carry out the scaling on based on the range that you yourself and you need for it to work out. Mr. Labod, you can't get -1. You can't get -1. All right. Thank you very much. Thank you. Let's go on. Let's go on. I also have Mr. Blessing and Mr. Isaac. If there are any questions that you think I didn't ask that you need to ask, just drop them there. They are also on the live chat. You'll be helping me as I go on, so we can meet up our targets. I want us to really understand why we are doing this. I know Mr. Isaac did a bit of it on Monday. Okay, everyone that can see. I'm happy that you guys are. In fact, I'm so excited. This is wonderful. Wonderful. 0.5 for me. Wonderful. Applause for everybody. I really appreciate you guys. Wonderful. Wonderful. All right. So let's pause a bit. I'll just pause for about 5 minutes. Maybe there are still some questions that you need me to clarify, or there's something like a gray area that you're looking at and you're not really. I just want you to know, what is going on here. Okay. Okay. That's Bola Joko. I didn't see your question. It says the normalization always falls between yes, 0 and 1. Yes, it's always between that range. It's never lesser than 0 or higher than 1. Normalization. Exactly. Thank you very much. Thank you, Jumoke. Thank you, Bola Joko. Really excited. You guys are, you are really, really, really. I'm so excited. So excited. Thank you so much. Thank you so much. I love your explanation. Love that. And I explained the normalization again. All right, I'll do normalization again. Let's go back. I said it is called what your minimum and maximum scaling. So you are trying to, what you do is that you have a range of, this is used for mostly numerical data sets. So all you need to go and do is what you go and pick your minimum, maybe in a particular feature. Okay, let's say feature like temperature. Let's take temperature. Okay. Okay, I should run the normalization. Just hold on. Let me explain the normalization. I will run the normalization calculation again. You have a feature. You know a feature. Maybe you have temperature for a feature, and a lot of patients, maybe like 10,000 patients temperature. Then the lowest temperature is maybe 10 degrees Celsius, and the highest temperature is 40 degrees Celsius. And let's say the middle temperature, you have 40, you have 60, then the middle is like maybe 40 degrees Celsius. So if you pick that, you just pick it. You go and pick the minimum temperature and the highest temperature. There's no how you calculate it. It will never go beyond. It will never go below -0 and what higher than 1. For when you are talking about yes, for when you are talking about normalization, it will normalize it all because you have followed the formula. The formula has said go and pick the highest feature in temperature. Maybe somebody has If somebody has temperature of 40 point something, the person is already dying. Because I think normal temperature should be between 30. Should be the highest you can have is 36 point something or thereabout. So when you are going above that, the person is already gone. Then maybe the minimum temperature is now like maybe 20 or so. That person also is in danger. Exactly. So I'm just trying to do that. So you want to normalize it to make sure, okay, I don't want to maybe sometimes it might have float number. Some temperature might be 36.2. But when you bring it down to zeros and one, all I need is that I need just these two numbers. The middle number is not really, immediately if I can get it that the range is between 1 and 0, then scaling it is very easy. By the time you are using it, it knows that the boundary is always between what? 0 and 1. 0 and 1. Exactly. Exactly. All right. Then Amarachi Grace, can you run the normalization calculation? You say, how can you find the main max when you have 15,000 numerical data set? Yeah, that's why we are using the main max. What's it called? Well, that's why we are using this formula. For this, because I supplied data sets. This is because I supplied my own data set myself. When you are doing this, you are going to be picking the data itself, your CSV data, and you are going to be telling it to pick the role of where you need. So automatically, it will pick the lowest feature, the lowest number of features, and the highest number of features. All right. Let me see what's that. Thank you. Python will do that for you. Yes. So I just did this one is me giving just three data sets. And this is a data. How would I call it now? My own data input. But you'll be using your CSV file. You'll be calling the row that you need or the column that you need. This everything you see it when the Mr. Blessing is doing it for you. So this is manual. This is just manual input. Automatically there's a code for where you pick, which you go there, select it itself without you having to bother yourself at all. How do you know X-Men? That's the same thing I've told us. I think I just said that now. I just said that now for peace. Using your formula, you will see it. You import this. Your data now will be your data scale. What's it called? Your data that you have downloaded, your CSV file. Then you will not call what you call the row. So this is just for the normal using a what? A normal input or a manual input. Manual input. Exactly. So that's just it. So you don't need to go and be looking at the 10,000 to 15,000 record and start looking for which one is the maximum and the minimum. We are doing in theory class is just to allow you to know that there are mathematical formulas what involved in this theory. They are not magic. And whatever is going on in here is not a magic. It's not magic at all. There's no abracadabra or whatever it is called. Exactly. So something is going on from a theory, from mathematical theory or physics theory or biological theory. Everything we are doing. Kindly rerun the calculation for normalization again. All right. I said that given this original data, I have these three data sets. From here, my minimum is 5. My minimum is 5, and my maximum is 15. And for my formula says what? For every time I want to calculate for any x, these are x values. These are x values. So don't get confused. All this is an x value, this is an x value, this is an x value. X minimum value means what? The minimum value in the range of those values, which is 5. X maximum is the what? The maximum value in the range of this value, which is 15. All right. So normalize the above. So for x is equal to 5, using that same formula that I've shown us. So this is our x. So we're picking x now when x is 5. Minus the x minimum, which we know that the minimum value for this range of data set is 5. Then divided by what? The x maximum minus the minimum value, which is 15 minus 5. 5 minus 5 will give us 0. 15 minus 5, which Deborah corrected me that that's not 0, is 10, which I appreciate so much. 0 over 10. Anything divided by 0 divided by anything will always give you what? 0. So the value for 5, when you normalize the data, it is 0. If we take 10, this will be 10 minus 5, right? Which will give us a 5, which will be 10 again minus 5, which will be what will give us 5. Let me see. Am I correct? Minimum value. Yes. That will be 10 minus 5. Then this will be maximum value 15 minus what's it called? Minus 5. So which will be what? 10 over 10. So when you give that again, or you divide, so you see, you keep on doing that. The more you pick those values one after the other. That is just what I'm saying. Do we always do normalization for all data sets? Not the old data sets. That's what I'm explaining to us. We are talking about features. A feature that you find out that it is not okay. Thank you, Drew. Thank you, Drew. Thank you, Drew. It's fantastic. A feature that you have found out that it is not meeting up with what you find out. How do you find out sometimes? It's not, before you even normalize the data. That's why Mr. Blessing says what we first do what we call EDA, which you guys are going to be doing this week. But I need to talk about this. So by the time you are doing your exploratory data analysis, you begin to understand, oh, this is why I say data needs to be normalized. This is why I say this feature needs to be normalized. So you find out that they are outliers. So okay, I think Mr. Isaac spoke on Monday. He said, just imagine having like a salary of 10 people. They paid, okay, let me just use 3 people. Somebody was paid 10,000 naira. Somebody was paid 15,000 naira. Then the third person was paid 150,000. If you look at it, 150,000, is it close to 10,000 and 15,000? No, it's an outlier. So how do you now make it for them to come into balance? By the time you use your normalization for it, it will reduce it to 0, maybe 0.5 and 1. So you have everything what in the same boundary. Because if you have to use 10,000, 15,000, and 150,000 to train my model, that gap is just too much. The boundary is just too much. From 10,000 to 15,000 and to what? To 150,000 naira. It's a very long boundary. But when I use normalization will break it down to 0, 0.51. Nothing will fall be above 1, and nothing will fall below 0. So that is just it. But sir, the lower boundary is not supposed to be lower than 0.5. I don't get what you're talking about, Razak. I said not lower than 0, not 0.5. It should be lower than 0. When it's lower than 0, you are getting a minus. You are getting a minus. I didn't say not lower than 0.5. I said what? You should not be having lower than 0, then not higher than 1. All right, let's go on. We're having our break by what's it called? By 8 o'clock, so I can feel our 10 minutes. Then you look at your standardization, which is also called the Z-score scaling. I know Mr. Isaac spoke about this very well on Monday. I saw his calculations for us. And he was talking calculating mean, calculating variance, and standard deviation. So all I'm doing is I'm just buttressing our points. Just buttressing what he has done and showing us the theory behind the calculations he has done. You just need to know. That. All right. So also called the Z-score scaling. It transforms your data to have a mean of 0 and a standard deviation of 1. It centers and scales your data for better performance in algorithms using normal distribution. So that's what it does. I'm not going to take time on this because I know Isaac has done that for us. So I'm just going to go straight to it. All right. So these are standardization formula. You have your what? S standardization. You have your X. Your X is your normal value. Why this is what? This is your mean. Your mean. And this is what your standard deviation. Okay, so let's go on. When do I use standardization? Use standardization, you can see the first one. We're talking about normalization. When you are talking about normalization, I said when your data does not follow a Gaussian distribution, you use normalization. But when you're using standardization, Your data is following what a Gaussian distribution, or you are using an algorithm that assumes normality, or you are talking about distance-based models. You are when you are using a regularization techniques. All this grammar I'm speaking are things that by the time you do your practical on Friday, you see that they are just grammars. But you just need to have an idea of when these are happening. Mr. Blessing is going to be showing you all this my grammar that you are saying in your data set. He will tell you. That's why you must always perform an EDA before you use any data set, which is called exploratory data analysis. Is my data balanced? Is my data a distance range balance? You will see it. You will plot a graph. You'll be using matplotlib this Friday. You will plot the graph, you will plot the scattered plots, a lot of different graphs. So you see the your feature, the way they are looking at. You see those that are closer to the range. You see those that are far beyond your range. You can use that. You can use Python to do that and see what your data looks like when you plot them in your scattered plot. You plot them in your pie chart, and your pie chart will tell you, okay, this feature has lesser, this feature is higher than this is lower than this. You see everything exactly when your features have different units or range. Then when you are using what dimensionality reduction techniques, exactly. So I'll go on. So this is your code for standardization. Almost so close to your what your normalization also. But it's called your standard scaler. I say what is giving you a mean of 0 and what printing what is standard deviation of 1. Somebody says scatter diagram. Yes, is that your scattered plots? You see all your features. You see how they affect your how they are being distributed in your what in the particular data set that you have gotten. So it's always but I was remembering the feature technique I was talking about, the chi-square. For those of us that are statisticians or that have done mathematics, you have your, some people say it's chi squared, some people say it's chi squared, whichever way, chi squared or chi squared. Then you have your ANOVA. Exactly. You have your mutual importance gain. These are all feature scalars that you can use to make your feature. You run this insert code contributor notebook. Yes, fantastic. Yes, you can pick it up. What I've done here, you pick it up. You see that what I've done manually, you also get the same answer. Everything I've done here with you manually, you just pick this up. This code, just copy and paste, and we are good to go. All right. So look at this original data now. I said we have a data of 10. This is my own manual input. Again, manual input. What is the mean? Easy to calculate mean here now. All I need to do is just add these three together and divide by 3. 10 plus 20 plus 30. Divide by 3. That is what? 60 divided by 30. 60 divided by 3. And then my mean. Then you know how to calculate your standard deviation. I saw Isaac showing us how to do standard deviation. So I'm not going to do that again. So those are the reason why I leave gray areas. I know somebody was telling me the last time, as Mr. Olajide, you don't tell us everything. If I tell you everything, you will not be able to do some things on your own. I'm not sure if they sent you the assignment 1 and 2 that I sent over. Is due for this Saturday. They are just simple. Everything we've done, I just put them in little multiple choice questions, just to let you know if you really have an understanding of what you've been doing. So these are things I expect us that after every class, you need to go back yourself and go and practice. You need to check this thing out yourself. So it's not just enough reading this tab, what's it called? These slides. You need to take down your own pencil and biro or whatever notebook you are using. Try doing your calculation yourself. If you cannot do your calculation yourself, use your Python to call import maths and calculate the standard deviation of 10, 20, and 30. So we need to try things out on our own. And that's how we get better when it has to come with anything that has to do with, in fact, anything, either product management, whatever course you find yourself, you must practice. All right. So I've gotten my standard deviation myself. So I say for what's it called? For X, which is 10. I've told us what your major what is X, your X are all your values. But this was my main. I minus it minus my mean, then divide by my standard deviation. I got minus 1.22. So what it's telling you is that for that, this should be called standardized data, not normalized data anymore. So what that is telling you that for those range of numbers, everything I have between those range of numbers must not go below minus 1.2, 0, and 1.22. By the time you finish plotting this, I don't want to waste time. You'll get to minus 1. You can go and try data and come and contest with me and say, hello, it's already wrong. I love that. But if I calculate everything for this should give us minus 1.22, 0, and 1.22. So that will fall between that range. So it means that you have standardized your data to give you that range that okay, that feature I want to use, and nothing should fall between this, below this, and nothing should go above this range. Why are you just doing that? You just want your features that you want to use to have meaningful impact on the model that you are training. Because when there's the range is too high, is higher than what it should be. So okay, we still have 5 minutes more. It gives your system problem, and that's why when people design models and they are getting 99% accuracy, and I'm wondering how come. In fact, for those of us that we've been doing this for a long time, when you see some reports of models, you just laugh and say, no, come. I did a work recently and I got 96, and somebody was saying, that work is fantastic. Is that? I sat down and I called Mr. Bless and said, this thing is looking somehow to me. He said, what do you mean? I said, is it? I've seen it. Yes, I know the person who did 98. I performed some processing. I got 96. He now asked me, said, you can still do some things and standardize this data and do something. So I went back and did that. Funny enough, the model that I was thinking was the best. By the time I used standardization for the model, I suddenly realized that it was performing. In fact, it was the worst. They had the worst performance. And imagine pushing that out and creating a what's it called? Creating an interface for that and cause problem in the health system. It will just be giving doctors and clinicians wrong diagnosis because I've not gone down to go into my data set to carry out every necessary things, remove all outliers, make sure that everything is balanced. One feature is not overshadowing the other feature, or one data set characteristics is not overshadowing the other data what's it called characteristics. When that begins to happen, you're having problem. And that's why you find out that for data analysis, for those people that have done data analysis, you find out that before you begin to draw out any insights, you do what you must what you clean your data set. You remove duplicate rows, you change ranges. Maybe some things are in float. You change if you see that okay, float will affect them. You change them to integer own numbers. So a lot of cleaning is going on. It's either you are deleting missing values if it's not going to affect the data set, but if it's going to be too much for a data of like 10,000 and you have like 9,000 missing, you might need to delete that feature entirely. But if that feature is going to have a significant what's it called impact on your final result, you might not need to okay what range is this? Okay, you might not decide to okay, let's use the main. Let me calculate with the main and use the main value for each of the values that are found. So it's a lot of things we are doing. So that's the same thing we are doing now. We've not started creating models, but we're just talking about how to just make sure that our data meets the required how would I call the standards exactly. Gives us our required standards. Okay. All right. So I just did a differentiation between your standardization and normalization so that you can just look at it very well. You can go back and check on this as also. I think this will help you so that you know, okay, this is when I'm using my Z-score scaling. This is when I'm using my min max scaling, which is the same thing. Z-score is standardization, min max is scaling. So you can see what is the output range. No fixed range, usually centered around your mean of 0 and standard deviation of 1. Then this one has a fixed range of 0 to 1, depending on how you have calculated it. But basically, I tell people I always prefer you just fix it within zero, zero and one. Sorry about that. The use case, I said was suitable for when your data follows a Gaussian distribution. Then your normalization, when you want all your features within the same bounded range, like I explained, within the same bounded range. What are they sensitive to? They are sensitive to what? Outliers. Both of them are sensitive to outliers. But it's just that standardization is lesser than normalization. Normalization is so sensitive to outliers that if you are not careful, one feature will destroy your model. You just find out that your model is not fantastic. So what are the algorithms that we use? When I mean algorithms, these are models. When do you use standardization? When you are using machine learning models, we usually use standardization most of the time. Somebody was asking me, I think I saw the question. Say where should we use? I think he was asking the question. I didn't follow that. Somebody was asking that question. When do we use that? When do we use? For what we are doing now, when it comes to numerical data, we're going to be doing more of what? More of a standardization for your machine learning models. But when we are going into deep learning and start talking about when you're talking about things like images and that, distance in images, working with pixels. Sorry, excuse me. We now begin to talk about normalization. Then when to use them, when the algorithm assumes normal, yes, just your algorithm. These algorithms, SVM, your support, vector machine, your logistic, your k-nearest neighbor model, your principal, what's it called, analysis, comparative analysis, and things like that. You need to talk about standardization because you are working with more of a numerical data sets. So then dependent on this also can be used for numerical data set anyway. You can, but because of the sensitivity, it's always best to use what standardization. It serves you, it serves you better than what you want to do. All right. I say choosing the right method. I just have to stress it again. So you just see it. So is everything I put in that is when you want your data to be between zero and one. Works well when your data doesn't have extreme values or outliers. Like I said, best for algorithms that depends on distances. When you hear the word algorithms, we are talking about your models also. These are models. These are models. Then ideal when you need the data to fit in to a what? A specific range. You can see like image data. So you know that your main mass scaling is your normalization. Like I said, it's always what good for your image data set. All right. Then your standardization, when your data has different units or large differences in range, works well if your data has extreme values. You now told you when the outlier is extreme, it will still work. So I said is what for your algorithms such as linear regression, logistic regression, also works with neural networks. But I usually tell people use standardization for numerical, use normalization for images. It gives you very, in fact, your life becomes easier. It helps you when you want to make all features have equal importance in the model. Yes, yes. There are times whereby you don't want to use any feature selection technique like your chi-square, your ANOVA, or mutual importance. I want to use all the features. So for you to use all the features, then make sure that all features are standardized. So no one is cheating anyone. Everybody is falling between the range, the mean, and the standard deviation that you are dealing to it. And you find out that models that come out being used this way, they perform better. Sometimes you see the accuracy like 85, and you're saying, somebody is saying, no, I did something. I got 90 something percent. Tell him to give you your data set. By the time you give him your data set, the person gives you this your data set and you find out that you just realize that the system will just show you, your model will tell you that that data was not rightly done. Nothing was done on it. Missing values were not worked on. It just exposes everything. So it's always good when you are creating a model. Make sure your data set is in the best form as much as possible. All right. I don't know if there's any question. All right. I've exceeded our time by a minute. So let's go for break so I can sign our attendance and then we'll come back. All right. Thank you very much. Okay, all right. Our break is over for now, so I'm sure we've been able to fill our attendance. And if possible, you've not filled your attendance, just keep looking for it. Keep looking for it. Keep looking for your attendance. Keep looking for your attendance. And just feel while we go on. We are the final part of the class. The final part of the class for this evening. So the final part of the class for this evening. So let's go on. So I've already spoken to admin concerning your assignment. So I think they are working on it at the moment. So let's go on so that we don't take much of our time. What I want to explain next is just a very simple concept. We're actually done for what we need to do tonight, but I just believe that for you to have taken your time to be here, so we must give you more than what exactly. So I appreciate it. A lot of us are just coming from work and we join the class, so it's fantastic. I really appreciate our strengths, our commitment. So I just want to talk about outliers. I've been talking and talking since outlier, outlier, outlier. Somebody will wonder what is outlier? What is an outlier? How can I even undo an outlier? Excuse me. So that's what this permits me. Let me just put what it is. So I say outliers are data points that are significantly different from the majority of other data in a data set. I think when I started, I was talking about somebody. Okay, let's look at Isaac. Isaac with the Highsheek. He has he has a white sheep, a male white sheep and a female white sheep. Then he brings them, crossbreeds them together, and they give birth to about 10 kids. You know, for lamb, let's call it a lamb, 10 lambs, and he was so excited. Oh, look at my lambs! They have gone there, and he just got there, and he saw one black something. I'm sure the first thing he will first move back and I have white sheep. How come there's a black lamb in their midst? That's like an outline. So what can he do? For animal now, that sheep is already black. What? Sorry, what can he do? What are the things he can do when it's that animal? It's an animal. I think what he will do is that if he doesn't like black sheep among the sheep, I think the first option is to trade and sell the black sheep, or he will eat the black sheep. So, but this is not for data. Data, you must find a way to make sure that this black sheep comes back to this place. This is your normal range where you want it to be. So this black sheep guy that Isaac has, he wants you to come here. But for sheep, now Isaac will either eat the sheep or what or sell it. But for data, he will not do that. He will bring it back here. And that's why we're talking about standardization and normalization. Uh-huh. Mr. Blessing was talking to me, was like, he said, this is fantastic for that. I'm talking about standardization and normalization at this stage. That he will use mean and what and median and this. And I said, that's fantastic. But so these guys have sat down here with the commitment. They need to give you what you need. Because by the time you are doing more of a complex, what's it called, modeling, mean and this thing might not work for you at that moment. So you need to know. So if I don't mention it, and you are like, what's happening? Fine, some of us will go through ChatGPT and look at it, and you will get it out. But it's good now you have an idea of what they do. But just try to undo this what black sheep. So the black sheep here is the outline. He's not on the same point with everybody. He has decided to stay on his own. All right. What are the characteristics of outlines? Like somebody was asking me, how do we know something is not standard, something is not this, something is not that? So now I'm talking about it. How do you know my data is an outlier or that feature is an outlier? I say it's unusually large or has an unusual small value. I told us. And that's the first thing you know. Like the temperature I've given you. You have been having temperature of like 36, 34, 36, 34. All of a sudden, you see 50. Then you are going through now, you see 10. You are wondering, how come 34, 36, 34, 36? Where's 50 temperature? Somebody is having 50 temperature of 50. Where is that coming from? Somebody is having temperature of 10 degrees Celsius. So you can see unusually, it's always significant. You see it yourself. It's always significant. That's why Mr. Blessing will always say, when you get your data set, when you load your data set, check the first 5 rows. I tell people, what may I do? I check the first 10 rows and the last 10 rows. In fact, it's easier for you at that moment to see your outliers. You will know they are always either at the top or what at the extreme. So you will see it there. Oh, wow, wow. Of course, there is you inspect it. You need to inspect. Oh, look at something like this. Oh. It means that there will be more like that. Then go to your last 10 rows also. You check it also. Oh, okay. And that. Then statistical deviation. The outliers often fall far outside the typical range of values when using what your statistical method, your mean or your standard deviation. Your mean or your standard deviation. They will always fall out or outside their range. So that's why Mr. Blessing said we'll be working this weekend, we'll be working with them. We'll talk about mean more for your practical, we'll talk about standard deviation for your practical class. So you see those characteristics. Let's go on. Then I said types. So these are the two major things I know. If I ask anybody who has been doing, these are the two things that we know that okay, this is an outlier. Okay. Then what are the types of outliers? You have the univariate outlier and the multivariate outlier. They are just English. Outliers that are extreme in one particular feature when viewed independently. Exactly. You just find out that that's the only guy. When you view all features, it's this particular feature that is just having funny things that you're wondering. Any other thing from name, from age, you fell into this, you got to temperature. I don't see funny. So on that column, on his own, independently, it's not looking good. So that's a type of. But when you now talk about a multi, it's one or two. So I'm trying to look. Okay, I need these 5 features. Like when I was classifying hemoglobin level for sickle cell anemia, and we hired Mr. Blessing and Mr. Isaac. We won an award from last year, October. We won 3 awards for that. We were doing that project. I had to see. We realized that there was some outliers. So we needed 5 features to calculate hemoglobin level. We just realized, what's happening? Why are they? So we're considering combination of variables. Exactly. And we need those features because they are important for us for predicting hemoglobin level. Is it high? Is it low? Is it normal or high? So it took us a lot of time, but we got it done. And the output showed that yes, the good work was done. And we won 3 awards for that. So it's always possible. In fact, they are putting it into deployment at the moment. So it's in deployment at the moment. So it's a lot of things like that. So you just need to make sure your data falls into what? Into your normal range. All right. What causes outliers? Exactly. Somebody will have asked the question, how come the outliers? Is mistake. Most of them are human mistakes. The first one is data entry error. Somebody wants to write 2.00, write 200, and he has been doing 1.4, 2.1. He wanted to write 2 point, maybe like that's what I was telling us, 15 data sets, maybe 15,000 records. The person is so tired and is thinking, I need to make no do so. And in the process of thinking of how he or she will put onions, carrots, and cucumber and lettuce into the noodles, boom, you forgot, and instead of putting the points, you're thinking of carrot and cucumber, put 00. It becomes 200. So human input. Then there's natural variation. So some values are naturally extreme, like very high or low measurement. Yes, if we pick all of us now and want to check our height, you'll be so surprised that if we all come together, there'll be somebody who is 4 feet among us. I know some people will say, no, it's not possible. You will see somebody that is 4 feet among us. Somebody will be 4 feet among us. Then somebody will be like 7 feet. I've not, I don't think I've seen somebody in 7 feet anywhere. I know my younger brother is 6.5 anyway. So it's very tough compared to our shop. So very tough. So extreme cases. There's somebody like me now. If you are going to sew a shirt for somebody like Isaac, maybe Isaac will take the shirt off for medium. If I'm going to sew a shirt for me, it will be like 2 extra large or 3 extra large. You can see extremely high, or somebody or small size, or somebody is using size X small, and what do you call it? X and S. So something like that. Then you have rare events. In some cases, the extreme values may reflect rare but significant events. Exactly. Especially for fraud, when you're talking of issues like fraud. And people somebody gives how come they are holding people for fraud. Is very difficult sometimes because some things will not seem like fraud. Whereas I love that system Mr. Blessing built for spam detection. Things like this happen also. So you need to check and make sure the data, because some data set will seem as if no, they are not, but funny enough, they are outliers. They are in the extreme, either low or what or high. So you just need to know. So I'm just talking about these things just for example. Exactly. Look at the example of an outlier. Can somebody pick out the outlier in this example? Consider the data set for house prices. You have 50,000, 60, 55,000, 52. You have 100,000, then you now have 5 million. Look at it. It's just ridiculous. Highly ridiculous. I want to check and see maybe there are comments for me. Highly ridiculous. When you're having things like that. It's highly ridiculous. So just look at it. So ridiculous that between 50, 60, 55, 52, you now have something as much as what's it called? Um 1 million, 5 million. Oh, thank you very much, guys. Wonderful. You guys are fantastic. You guys are fantastic. You guys are fantastic. Great, great. I love this. Fantastic, guys. Thank you, everybody, this evening. You guys are sharp on point. So I said the value 5 million could be considered an outlier since it is far. Now somebody will now begin to understand, so we need to normalize now. So all I need to do is okay, I want to normalize or standardize. Oh, this is the minimum, Abi, 50. This is the maximum. Then I use my normalization, what's it called, technique. By the time I will do this using my normalization, I will get my what? What? One, my 1, 0, 0.5 or my 0.5 or 1. Exactly. So if you take this now and use your normalization technique, you find out that you will not bring them together to the same rate. So this guy will not affect it again. I will just say for everywhere we see 5,000, we know that it is 1. So anywhere we see 5 million, it is 1. So you have done that calculation and you are good to go. You are good to go. All right. So that is just it. I just wanted to explain some of these concepts to us so that you really understand what I was talking about, because I'm not some people are outlier. Why is it calling outlier? Those are things that make us to use what standardization or what normalization. Thank you. How do you now undo them? How do you undo these outliers? You can't undo without identifying it. And that's why I said we are going to do EDA this week. So some of you will be I so love EDA. Especially when Mr. Blessing is doing it. He has some very, very fantastic way of doing this EDA. I just so love them. And I'm stealing part of these ideas also, and I use them. So I'm confessing. They're fantastic. When he does his EDAs, you just fall in love with it. You see the way your data looks like, you see your scatters plot, you see convergence between features, you see divergence between. It's always fantastic. So the first thing you need to do is what you visualize. In fact, it's very wrong for you to just take data sets and load it into a model and start training when you have not done visualization. You see, are there outliers in my data set? I think Mr. Isaac was talking about box plot on Monday. I use more of histogram and scatter plot myself. Mr. Blessing does that also. He was talking of box plot. You will know. You will see the box plot is the one that he drew that looks like a car on a line or like train, like the body of a train. You will see outlier. You see some will be on top, red. The ones that are normal will be green or blue color. You see that you really want to put the color code. Anyone that goes beyond this range, put them in red. You see them. You see some will be far away. You'll be wondering These are the baseline of 0 and 1. What are those guys doing there? They will always be there. Like the scatter plot I showed you, you can see all the green ones were on that range. The red guy was somewhere else, which is the black sheep. So you must first plot. You must if you're using your math plot line. It's called your math plot line. You use for visualization. So you plot to visually identify your outliers. Then other ways are using statistical what method, which you can use your interquartile range or your Z-score, which is the one like this standardization. So what do? You look for the mean and standard deviation, and you are good, and you are good to go. You are good to go. So that's just it. Then you want to remove. When you've identified, you must remove. When you are talking about a remove, you are standardizing it or whatever. Exactly. So if the outlier are due to data errors or are not relevant, yes, like what I was telling us, there are some that you just find out that the role is not okay. I want like when I was doing hemoglobin level classification, this thing. We didn't need age because we are not using. We didn't need the demography. We didn't need the demography. The demography came in 1 and 0, and honestly, nobody put description when I checked the data. When we checked, nobody put a description to say 0 is male, 1 is female, or 0 is female, 1 is male. So it was giving us confusion. How do we now? We even be checking the names one after the other. Data set of over this thing. All we just did was we just deleted and ignored the what's it called? The row for age. It wasn't necessary because I didn't need age at that moment for what I was doing. I was just looking at I wasn't doing a comparison of what age we wanted to know was people with sickle cell anemia. What makes their health issues aggravated, their hemoglobin level. That should be between a range. When it's lower than 12, then there's a problem. When it's higher than 15, there's a problem. So that was what we were looking for. So we didn't need the age. So we just wanted to know our patient. So I say you can remove that row containing what? The outliers by using the conditions based on what? The IQR scores or the Z-scores. Yes. We just found that it wasn't important. We chopped it off from that list. All right. Okay. Then you can cap or keep your outlier. When do you do this? When do you can I hide? Can you click to hide and the lower part of the screen? All right, sir. Thank you. Ooh, what did I do? Sorry about that. I think I mistakenly closed the. Did I do something? Sorry. I will see. Sorry about that. Sorry. Sorry. It's taking. I'm hiding it. It's hiding the whole sharing of the screen. So sorry about that. All right. So capping or clipping the outliers. When do you use it? If you want to keep the data but reduce the impact on the extreme value, you can set up what? Set an upper and lower bound and limit the outliers to that bound. Exactly. Somebody was asking a question and I give some random range. I said, for instance, if your RQR method suggests a lower bound of 5 and an upper of 50, all your values must be below, all your values below 5 will be set to 5, and all your values above 50 will be set to 50. So I've answered your question now. Sorry, I've answered the question. So you can at that moment, if you feel that that's what you want to use, but you must always be careful when you're referencing that in your model training that you have set some higher boundaries to fall between that range. If not, your model will misbehave during your training process. So I am always very careful. Mr. Blessing always tell us, always just key to your mean, the standard deviation method, and standardization and normalization. So it gives me peace of mind. The range is already between 0 and 1, so I can go and do a lot of. Thank you very much. Conditional formatting. God bless you, Mr. Aladeola Dimeji. I really appreciate that. And so you can do that You must not forget, because if you have reference, so that by the time you are calling up your you're calling up your training when you want to split your data, you must be able to not to forget that I've set some conditional. So when I'm splitting my data, I must split and make sure that it's a balanced split. If not, your outliers will come up and give you problem again. And you just find out that you're not getting what you need to get. All right. Thank you, please. Thank you. Then you can transform your data. You can transform the data. For continuous data with large deviations, I can use logarithmic or square root transformation to reduce the skewness, exactly, and bring outliers closer to the other data point. This one is always good when I'm doing image. This is always good for imaging. So let's go for imaging. So I just bring the skewness. How far is it from? I just make sure, okay, like somebody says that reduce your Mr. Dressing what they say, okay, if you have a 3D image, say Mr. Gide, so that you don't give yourself problem. Convert your 3D to 2D immediately. So you bring it back, you put it to two dimension, so that everything becomes falls in the same data point. So it's always good. These are things you'll be saying, you transform. So a lot of ways you can undo outliers. Then input outliers. When do you input outliers? Somebody will wonder, we are trying to remove, we are inputting them. If the outliers are important, but need to be replaced with more reasonable values. So how you can replace the outliers with the median. Like I said it. This is what people do. Most guys in data analysis. When they see those things, they just use mean or median to avoid extreme values affecting your model. So they all say, you see some maybe like 2.5, 2. And when result, they see something like, and they need to use those. Okay, let's calculate the mean. Then for everywhere we have extreme values, you just input the mean, and your model is standard. So at least 2.5 to between, when you look at 2.5 to 100, it's so far away. But 2.5 to like 4.5, it's still okay now. Excuse me. It's fantastic. And we are good to go. Then use a robust model. This is where people like us we do. If you just see that I don't want to remove or transform any outlier, he said this guy, you see these three base guys, random forest, three base, and this logistic regression. That guy is something else. There's no how your data set, and I've not seen it. Logistic regression will work. Mr. Blessing will tell you. I don't know whoever I build that model to be able to undo outliers on its own. But if you know that you are not using these three base, and what you are doing are maybe they are distance related, you will need to what to carry out those processes. But when you are working with some data set and working, let me try logistic regression model or use random forest or tree based models. Naturally, they are less sensitive to outliers and they will handle them. It will perform its own outlier removal or whatever way it wants to do it on its own without me having to do any stress. Any stress. I'm sure somebody will now say, you're not teaching us all these things when they are models. You need to know some things, because if you don't, it's just like you are cheating yourself, because you will fall into some issues whereby these models might not be. You'll see when I'm talking about next year, I think is this week or okay, fourth week or the fifth week, and I'll be talking about choosing models. We'll now be talking about why we should choose models based on data sets. And you now see, okay, I don't just go and pick any model and use. You don't just pick any model and use and say because I've seen the model. You will know when you are to use a regression model, when you have to use a classification model, when you have to use a bimodal model. So a lot of things like that. And somebody said exactly what I was about to ask. Isaac, I beat you to it. I beat you to it. So you begin to see that. So that's fantastic. I'm glad you're thinking like that. Thank you very much. It's not always good to use shortcuts. Exactly. Learn it the other way. It will come handy. So when you know it, so that you don't start when you start with shortcuts, then one day you have problem and somebody is saying you didn't do that, you will not look lost. And one thing I don't like, I tell people in what's it called? Tech. Don't let people see you as a fraud. It becomes painful because You will lose integrity, you will lose trust. Don't let people see you as a fraud. Know the rudiments of everything. So that's why I put this there. I would have, if I wanted to start, if I wanted to do some guys that say, okay, I want to know it now. I'll tell him, okay, you want to know it now. Teach me in 1 week. Okay, I say, guy, go and bring 500K. I'll teach him. I'll just go and teach him all these things and take him all around and put him fast. Ah, I can code. The day we fall into trouble, you come back and meet me again and say, well, is it worth it? I say, okay, pay another 300,000. I will teach you. You keep bringing, does it make sense bringing you to come back to me? It's good you also know it and you go out and train other people. So that's the beauty of tech. You can't know everything. In fact, it's not good to think that you know everything. Share your ideas. People can go out and come back. Ah, this person told me I know this, and you too, you can go around. It's like a gospel. You're touching other people's lives. So good, well said. It's not always good to want to use shortcuts. All right. Final thoughts. Scaling is critical in many element models. Yes, very critical. It improves accuracy, speed, and performance. So you must always remember to choose methods based on your data distribution and model type. This is what we'll be doing upper week. I'll now expatiate on this very well for every one of us. All right, I will lose my day. Okay, now that's not part of what we're talking about. All right, so let's throw in our questions. Let's throw in our questions. Okay, and see and see. Is there any question? What do you think? And I can use this opportunity to also talk about some things I need to talk about to the class also. I think it's part of learning also. All right, I think I'm on the chat group. Let me see. Let me drop my screen. I can see the chat group. I can talk. Okay, I think everybody can see me now. Fantastic. All right, any question? Any question? All right. Somebody is saying this talk about PCA again. Like I was talking about, I said PCA stands for Principal Component Analysis. You must understand that it's not a feature scaling technique. You must understand that it's not a feature scaling technique. It's just reducing your dimension of your what's it called, your data. But most of the times it's usually what's much more closely related to feature scaling because proper scaling itself also it's almost like the same step. You are applying the step of principal component analysis. You are reducing your data dimension. You are removing outliers. You are cleaning missing rows or row mismatch and things like that. So it's just almost the same thing. Somebody will ask, okay, why is now feature scaling better than what's it called? Better or why do we do feature scaling before we talk about principal component analysis? The issue is that PCA is always sensitive to scale of the feature. It's always talking about scale, but more than that, we are not talking about scaling alone. And we are not talking of just that alone. We are talking more of what the dimensional, the robustness, exactly that's the word I'm looking for. The robustness of the data set to its that we have set what our model to actually do what we want it to do. So it's just beyond that. So I tell people instead of talking about a principal component analysis, do feature scaling. You are good to go. Just use your standard scale and your standardization. So you might not need to do principal component analysis. Exactly. You don't need to you don't need to do that. Please somebody said no question. Please let me look at I'm using my other phone, so I'm looking at your sorry. Let's look at it. Thank you. Perfect business. What are the job opportunities of this course? I will talk about that, please. I'll talk about the job opportunity. Please remind me before I end this class. I'll talk about job opportunity. I wish you can explain the step of standardization and normalization again. Okay? Which other one you do? Somebody was talking about the Gaussian distribution. Gaussian distribution. Wait, let me go back to Gaussian distribution. What I was explaining to us, I said when you talk about something with Gaussian distributed, what does it mean that the data is Gaussian distributed? The data is skewed. I told us we call it long tail data. It's an extreme from what it should be. That's just it. Then it might have two peaks, it's bimodal. It's not carrying just one value, it's carrying more than one value. Two different extremities, very low, very high, like this. Very low, very high extremities. Then it has outliers. One guy will just be, you know, floating on his own. Just like the example that I showed us. You have 10,000 for house prices. You had 50,000, 60,000, 52. Then we had 5 million. No, that's an extremity. Then when it's Gaussian distributed, it may be uniform. Yes, most times they might be uniform. So that's just what a Gaussian is all about. It's all about. All right, what again? What again? Normalization and then standardization. Okay, let's go back to normalization and standardization. Normalization. I said normalization always rescales a value to zeros and one using what? The minimum value on that row or that column and the maximum value. So just like the house price I explained to us, you have the minimum price for the house for 50,000. They have the extreme for 5 million. If we use our standard normalization formula that says your price minus the minimum price divided by the maximum price minus the minimum price, you will see that you will get between what? The range of 0 and 1. Nothing, you will bring everything. No matter how high, let it be 10 million. If you bring it down. So by the time you plot your graph, every feature, if I plot a graph of 50,000 naira and 5 million, if I'm not careful, it will fall away from scale. But when I reduce everything to 0 to 0.1, you will see your graph will form from 0. It will pick like this. Let me share my screen again so that I can show us what I'm talking about. Let me share my screen with you so that I won't waste time. Let's share screen. Sorry about that. So you can see what I'm talking about. Okay, open my screen and share it. Okay, waiting for my screen to be shared, please. Can we all see my screen now? Can everyone see my screen? No. Admin, please enable me to share my screen. I think I'm already sharing the screen. Let me so that I can share my screen. Not yet. Let's hold on. Let me look for other questions that have been asked also. While the screen is coming up, see other question. Somebody is saying differentiate between. Let me see that. Let me share my screen. Okay. Differentiate between outliers and Gaussian. Differentiate between outliers and Gaussian. Okay. I think I explained this the first time also. Okay. But I'll do that again since we are asking ourselves questions. I think we can be on the same page. Same page. Wait. Wait. I'm trying to share my screen, but it's not giving me anything. So just please listen to me carefully. All right. Like I've said, what is the difference? It says the first thing you need to know first is that outliers and there are two different concepts. Two different concepts. So, but I said it the first time when I was explaining, I said they are often related, but they are not. They are not. For Gaussian distribution, it's theoretical probability distribution. like a mathematical distribution where you talk about your mean and standard deviation. And I say that's where you always need to use standardization. But for outlier, you are looking at data points. You can see that why is my screen not sharing? As when I showed you the graph of the outlier, you could see that we have a graph of y and x axis. The distribution of the data, they were on one distribution, but the outlier guy went somewhere else. Let's imagine that straight line that I drew was at distribution A. The outlier was at like a point. Let's use point Z. Let me just use point Z. You can see that it's different. But when it comes to Gaussian distribution, it's just like what's it called? A relatively probability, exactly. Probability of it is like more of mathematical. What's the probability? Is the shape of the data, are they following the same way? Aha. Is it okay? Let's okay using the mean and the median, exactly. Mean and the standard deviation. Is it close to the mean and the standard deviation? Is it far away? So that's statistics. It must always deal with what? With the mean and standard deviation for Gaussian. But for your outlier, it's dealing from one point to the other. Why I says always make sure you make it zeros and one. You will decide from 0 and 1. And when we spoke about the conditional, somebody who gave me that name, I was so excited. Conditional. I cannot decide, okay, if I don't want to use 0 and 1, nothing should go below 5 and 50. And anything that's above 50, let it be called 50. So you can see that we're using points for that. But for Gaussian distribution, we are relying, that's the word. We are relying on what mean and standard deviation. Exactly. So that's it. Then which other question again? 15 minutes more. 10 minutes more. Please, where do we see? Like the assignment have told us, admin is already working on it. So please let's leave that. Admin will get back to us. I've already messaged admin and they said they are working on it. So let's bear with them. Bear with them, please. This thing is moving very fast. Moving very fast. Moving very fast. Oh yeah. Yeah, as an AM, somebody said, what is the major difference on a data science? Yeah, a data scientist now. We are just you. Oh, your question is just so funny. I love it anyway. So what's the difference between a data scientist and an AI ML person? Can anybody help us out before I go on? I will talk about it. Who can tell us? Is there any difference between somebody who is doing AI ML and somebody who is called a data scientist? Quickly, quickly. Who wants to answer? I can't see our. Is anybody answering or everybody? Nobody wants to answer. Caroline, thank you also. Thank you for listening. I really appreciate you. Thank you. Thank you. Mhm. Okay, good. Ogochukwu says a data scientist must know AI and ML. Goodness says I have not seen a difference yet. I need more answer. Olabode says it is the same. Mhm. The data scientist is not training model. Okay. I'm seeing interesting things. So yeah, go on, go on, go on, go on, go on. Go on. Okay. Mhm. Okay, great, great. I love this. I love what I'm seeing. Go on, go on. An AI person train and develop the model. Okay. Data science is about using the data to make decisions, while AI is using the data to create. Okay, let's go on. Let's go on. Data science based on data visualization, and AI deals with. Okay, okay. I will tell you, sir, you can't be an AI ML person. I love your answers. Everything is correct. Model creating makes the person do. Okay, fantastic. I love that. I love that. Yes, output and input for okay. Collect what is easy to train the model that can learn. Okay, great. You can't be an AI ML personnel without being a data scientist. We are all doing the same thing. The only difference between the AI ML and the data scientist is that the AI person, after the model has been trained, you ensure that what the model is deployed for usage. Data scientists will do everything, clean, scale, do feature engineering, test splits and everything, um, carry out whatever normalization, this thing, train the model and evaluate the model. Oh, okay, this model is working fine. AI person will also do the same thing. AI ML will do the same thing. That's why we're doing AI and ML. The ML part is the data scientist part. The AI partner is not the deployment. You deploy. You now need to deploy the project. And that's what Mr. Blessing was saying in the first class. He said, we are not just only going to build a model. See, I'm going to show you how to deploy the model for usage. So AI comes into deployment. Somebody built ChatGPT, trained it, but somebody put it in an interface to say you can use it. So that's just it. There's no, we are doing the same thing. One person just go before somebody. The AI is more of like an engineer. And that says, okay, this model that you have built, we need to put it into the real world now and see what to give us. We need to work on it and that. So that's just it. So they are both doing the same thing. One person is just going a step further. Like for you now, when you do your project now and you create a system, some of the time, some of us will do a lot of projects that they are in the library, nobody has used it. For me, Mr. Blessing and Isaac will come up and pick it up and say, wow, this is a lovely project. Let's deploy. Let's put it into the world. So we are more of AI people because we want to see the usability of that model. We're not just creating a model that will not do anything. So that's why we are combining together. Every work that you have done, every model you are going to build in this class for your project, it must be deployed. Either you are building a web interface to access it, you are building a Flask interface, you are using Django or anything, you are going to be doing that. So not just enough for us to clean the data set, draw out insight from it, train the model using the data set, select the best model. No, we must show, and that's why Mr. Blessing showed us that first interface when he was talking about detecting spam mail. You put it, you tell you type the word inside, spam mail detection. So it's always fantastic. Awesome. I love you guys too. Great. I love that we are learning. This is fantastic. Mm. Deployed. God bless you. God bless you. I love this. I love this. Yes, it shows that we're having a broader understanding. Maybe I have time to read. But the broad field way involve collecting, cleaning, analyzing, and interpreting data to get correct. That's good. That's good. So would we learn how to deploy? Yes, we'll be teaching you Flask. Yes. Mr. Blessing and Isaac will be teaching you Flask. So you will deploy. You are not creating anything that you can't put in your wardrobe. God forbid. God forbid. We are new generation data scientists. We are not doing work that we are abandoned. So that's why I tell you, Mr. Blessing says, no work is useless here. No work is useless. Everything, everything you do, your project, you will deploy it. You will do presentation for us. You will assess and be sure that your model is viable. We will tell you where you need to tweak and do some hyperparameter tuning or you need to correct some things. Okay? So it's a lot. It's a lot. So that's why you have 2 weeks for lecture. Then we now have the remaining 8 weeks for the whole lecture. Then we now have another 4 weeks for mentorship and project presentation. So within that process, we'll be teaching you marketing. What are your markets? Somebody was asking a question, where do I get job opportunities? All those things we will talk about them. It will be for you for that 1 month. Okay, I'm doing this one. My model got stuck here. Something happened here. Okay, we'll create a Zoom meeting with you. Look at this, look at that. Take this off. Suggest to you. We will not be giving you the answer. I'll be suggesting. So it's based on what you want. Okay, so I think you should do this. With, Mr. Isaac, you say, okay, I think Mr. Blessing will say, I think you go back again and go and work on it based on what you think or the information we're giving you. So it's a complete package. I think we should say thank you to DSA. We should say thank you to the probation of. It's a good thing that they're doing for us at this point. So we should really appreciate them. I think we are true for today. We still have about 7 minutes more. About 7 minutes more. Is there any other question again? Any other question? What does it mean when some values are negative after calculating standardization? It doesn't mean anything. All it's telling you is that it should fall between that range. So you know when we created that standardization and what's it called? Sorry, the mean and the standard deviation. So it's telling you that your range can fall between anything minus 1.2. But immediately it goes below that minus 1.22, the problem is happening. Immediately it goes higher than 1.22, there's a problem. It's just a range. There's no issue. All you are saying, I'm saying, let everything fall away. Thank you. Those of you that are saying thank you, Incubator, thank you, DSA. It's wonderful. You need to keep thanking them. You need to pray for them. They are doing a powerful work in Africa and all over the world. So it's a wonderful thing. These are courses that people pay about $500,000 for. They are doing it for free of charge. So I really appreciate them. They are doing very well. Doing very well. So that's it. So please try to. I love today, and in fact, I really I should give everybody a round of applause. You are did very fantastic today. I love you. You challenge my brain. I challenge you also. So it's a fantastic day. I enjoyed myself. Enjoyed myself. All right, everyone. I think I will call it a day today. Even though we have 5 minutes more, we're done for today. Friday, get ready. By now, and I encourage us. If you know that your what's it called, your Anaconda Python is not working, reach out to myself, Isaac, and Blessing on LinkedIn or email. We'll schedule a quick meetup with you before Friday. Set up your Anaconda for you. Set up your Python for you. Do some testing for you to see that it's working fine. Because now from this third week, the work has started. Anything you're learning from Friday now, begin to pay attention because we're already teaching you processes on creating your model, how you'll be training your model, testing your model, selecting the model you want to use. So let's get ready. So the rework has started. Talk is reducing. Rework is starting now. Just little theories, more of practical. So it's good to have you guys here today. Thank you also. Thank you all. I really appreciate you. I learned from you. I learned from you. You guys keep, making my brain. Make me read more, do more. Thank you so much. All right. Take care of yourself, everybody. All right. Have a beautiful night rest and see you on Friday. All right. Bye.